Hi, now let's continue with autoencoders. So autoencoders are simply feed-forward architectures. It's another type of architecture which has the following characteristics. First of all, it has a bottleneck layer in the middle. You can call it a code, you can call it an embedding, what have you. The important thing is that this bottleneck layer has fewer dimensions than the input here. It has an output layer which has dimensions that match the dimensions of the input. So the output has to be basically equivalent in size to the input. And in the end, we have an objective to reconstruct the input using the output. So basically we want to train our neural network such that our output looks as close as possible to our input. Autoencoders basically comprise two networks. First, we have the encoder network, which takes our input variables and embeds them on a code, on an embedding, using nonlinearity H. So basically very similar to what we've seen so far with feedforward networks. And then a decoder network, which takes as input the code V and projects it back on the space of our inputs. X prime then is of similar dimensionality like X, and we can compare X prime and X, and therefore generate a loss. One straightforward way we can compare the two outputs is, for instance, using the Euclidean loss. The weights are often tied together in an autoencoder. And again, it's very important to have bottleneck. If there is no bottleneck, so basically if the number of dimensions in our middle layer are larger than the number of dimensions in our input, it means that basically you can copy the input through the so-called bottleneck to the output, and then you would have perfect reconstruction, right? Like you could do some sort of smart combination of the identity functions, then you wouldn't really learn anything and you would attain zero loss. However, that zero loss would mean nothing, would be trivially obtained. Therefore, it's very important to have no bottleneck. It's important to have bottleneck, and if for one reason or the other we need a large number of dimensions, it's very important that we put a regularization constraint or another constraint that makes sure the neural network cannot just copy the inputs to the output right away. Autoencoders often can overfit, or basically they can fit very well on the training data. They cannot really, it's not a very hard task. So one thing that can be done is add some noise to the input, and in that case we would ask the autoencoder to still try to reconstruct the original signal X regardless. So the model doesn't really have access to the original signal, it has access to only a noised up version of the original signal. However, it can attain zero loss only if it tries to minimize the reconstruction, the distance of the reconstruction to the original signal regardless. That way we make sure that we learn more generalizable embeddings, and the reason is that the neural network cannot learn to fit too much to the added noise, because the added noise will always provide some extra disturbance on the input, and by just blindly learning it, it will never be able to obtain very low loss in the output. Of course, we can have an autoencoder with a single layer, but we can have more than one layers between the input and the output. That way we can obtain deep autoencoders, and in that case the neural networks of the encoder and the decoder learn to embed the data in some form of a high dimensional and nonlinear manifold. Compared to PCA, deep autoencoders learn better embeddings due to the nonlinearities involved, and this is very interesting because in fact autoencoders can be used to learn compression, and they can be shown that they're very similar to the PCAs, to the PCA. In fact, they actually learn the same subspace like PCA, like principal component analysis. So in a way, linear autoencoders, that is autoencoders without having non-linearity, basically provide the same solution like principal component analysis. Autoencoders can also be used for visualization as well as for pre-training, because we don't need label data to train an autoencoder. What is important to realize is that the autoencoders are not probabilistic and not generative models. So of course we can try to put in our code new coordinates, so new types of input, but we're not guaranteed to generate anything meaningful. Most probably we're going to get very patchy types of generation. So again, they are not probabilistic and they're not generative. They can reconstruct the input, but they cannot really generate new data points. For this, we need variational autoencoders that we're going to be discussing in the following sub-lectures. Thank you.